Hello everyone, I'm Quentin Demoulin and today I will be presenting wing 3D reconstruction by constraining the bundle adjustment with mechanical limitations. So this work is part of the PhD I'm working on with Airbus in collaboration with the laboratory TESA, IRIT and the school ENP and SAIT. Before going on, let me introduce myself. I received the engineering degree in telecommunication with a major in high-tech imaging from the school Télécom Sud Paris in France in 2017, and I am currently working for Airbus Flight and Integration Test Center as a PhD student from the University of Toulouse. That being said, let's jump into the subject. If you've ever been on an aircraft and looked at the window, this is what you may have seen. During flight, the wing of an aircraft are submitted to efforts that creates twist and bending. Those deformations are foreseen by theoretical models that should be evaluated and improved during the certification phase of the aircraft. Now, the problem is to estimate the 3D shape of the wing from those types of views with grazing angles of views, restricted camera position, illumination changes, or even camera motions. In this study, the proposed solution is to use a set of cameras installed at the window positions and on the vertical stabilizer here to reconstruct the 3D shape of the wing using photogrammetry approach. So in this presentation, we'll first have a look at this photogrammetry approach with an introduction to the photogrammetry basics and the algorithmic chain proposed. Then we'll explain the new method that we call the constraint bundle adjustment that exploits mechanical limitations of the wing to improve the reconstruction estimation. Finally, we'll have a look at the experimentations and results. To introduce the photogrammetry approach, let's start with the basics. Let's consider a set of 3D points xi that are observed by 3 cameras here, and the 2D projection of those points onto the cameras are called xij. Here the first thing you will notice is that each camera has its own coordinate system, which is different from the aircraft coordinate system. So the first thing we will do is to transfer the 3D points from the aircraft coordinate system to the camera coordinate system. To do so, we will use the camera matrix Pj that models the camera rotation and translation, represented by a vector alpha j here with the rotation and translation. This camera matrix is actually a rotation and a translation here. And once the points are transferred to the camera coordinate system, they are called Lij here. Then we will project those points onto the 2D images using a new matrix Kj that represent the camera intrinsic parameters, so the focal, the sensor center, or the pixel size. This camera matrix K is known from the calibration process before flight. And in the end, we've got our 2D projection of the points depending on the camera parameters and 3D points with this expression here. Now the problem is how to recover the 3D position xi and the camera matrix pj from the observation points xij. So there are several resolution possibilities. First of all, you can consider that the camera matrix are known, or you can also add constraints on the 3D points themselves. For instance, you can say that we have non-deformable solids. For the moment, we will stick to the generic method where we remove the aircraft coordinate system and work only into the camera coordinate system. Then you will try to find the camera matrix Pj and the 3D point xi that minimize the reprojection error. That means the distance between the estimated point projection xij hat and its observation xij on the image here. So to be clear, if you estimate the 3D position of x2 here with some error, when you will reproject the point onto the 2D image, you will find an estimated projection with some error with respect to the observation here that we will try to minimize. This is called the bundle adjustment. So this problem is highly non-convex and non-linear and can be solved using iterative methods such as Gauss-Newton or Levenberg-Marquardt that rely on the Jacobian matrix for the step calculation of each iteration. Conveniently, one interesting property of the bundle adjustment is that the Jacobian matrix is sparse. A projected point only depends on the corresponding 3D points and cameras, which is written here. So to be clear, for the first point observation, x11, it will only depend on the first camera here and the first point. So all the other elements of the row will be 0, and it goes the same with all other observations. This will greatly improve the calculation of each iteration. Now to apply the method to the case of the wing, since the optimization is non-convex, we will initialize the camera and 3D positions of the points using a drone scan of the wing. At the same time, we will calibrate the cameras using pictures of a chessboard. Then to obtain the set of observation xij, we can use natural features of the aircraft plus line detections or markers plus graduation detection, allowing a subpixel detection. And when we apply the bundle adjustment, this is the kind of result we can get from the graduations and markers. Now the question is how to transfer the points back to the aircraft coordinate system, and to do so we'll use an additional camera at the rear of the aircraft that looks at reference points that we consider quasi-static during the tests. And since we know the positions of the reference points, we can estimate the transfer matrix Q from the aircraft coordinate system to the rear camera. Since this camera is also part of the bundle adjustment, we can estimate its parameters alpha r, and from this camera we can register all the 3D points and camera coordinates to the aircraft coordinate system using this expression here. And here you got the results after the registration phase, where you can see the set of 3D estimated points overlaying with the 3D model of the wing on ground. In conclusion, so far we allowed camera and marker motions and introduced no prior knowledge about the wing deformations. However, it is still possible to use prior knowledge about the aircraft mechanical limits to improve the wing reconstruction. This is what we call the constraint bundle adjustment. During the flight tests, we know that the wing won't suffer any damage, so we can think about some constraints. For instance, if at one step we've got 2 points with a distance L0 and at another step a new distance L which is too big with respect to the first one, we know that it is not possible. You can also think about other constraints like bending that will cover 3 points at the same time. And here you can see that you cannot have bending too big at one step with respect to the other. So we can think about a set of constraints, such as the volume limits, which says that a point has a specific maximum volume. Then we can think about bending limits. For each point we'll have limits within which the bending will range. So we'll say that the bending is the second order derivative along the y-axis. And we can think about other constraints such as torsion or elongation. Using a set of points on the aircraft surface, we will translate those limits into numerical constraints. So here, for instance, we said that points stays in a disk with respect to their initial position. Or here we can use a finite difference to calculate the second order derivative. So it gives us two inequations here. And now to extract the mechanical limits, we will have a look at the ultimate loads. The ultimate loads are the greatest effort that we can apply to a wing while she stays in one piece. So using finite element method, we can recover the 3D shape of the wing under those ultimate loads. and this is validated during the static test here. Then from these tests we will extract 3D shapes of the wing for all possible ultimate loads. We will process those shapes and create our set of constraints. Finally, the constraints are expressed as regularization term to penalize the objective function of the bundle adjustment. So here we will have the constraints at the end of the bundle adjustment using the current Beltrami penalty function to enforce differentiability. So we use this function here. This means that when we are within the mechanical limits, the penalty will not be activated, and once you go outside the mechanical limits, you will have a penalty term. Then what is also interesting here is that we will conserve the sparsity of the Jacobian matrix. So here for the constraints, you see that for the volume constraint, for instance, it will only depend on the rear camera, which is here, because we have still the registration phase, and also on the point itself. Now let's have a look at the experimentations and results. Here, this is a first experimentation we've done on ground on an A350. So you've got markers installed on the wing surface and graduation on the lanes here. We've got cameras installed at the window positions. They are installed 1 meter above the windows to simulate the views that we'll have during the flight when the wing will be bent. A first step was to calibrate the scene using a drone scan, and then you've got the views from all the cameras. Finally, we shook manually the wing tip to create a motion of about 5 centimeters amplitude, and when we reconstruct the wing, this is what we get. So here you can see the reconstruction with a motion magnification on the z-axis, and even if it's a bit noisy, you can clearly see a 5 centimeters displacement, which is really good for what is required during the test. So now if we look at the results from the constraints bundle adjustment, here during the motion sequence you've got the motion of a point at the beginning of the wing, and here at the end of the wing. In blue you've got the reconstruction without any constraints, and in the other colors you've got the constraints mentioned earlier. So what you can see is that with the volume constraints you've got a really good sinus here, also with the volume and the bending, and this sinus is coherent with what we introduce in the end of the wing with the 5 centimeters amplitude. When we look at the bending alone, you can see that there are errors. It is due to a loss of scale. From the previous results, you can think that only the volume is required, but actually, if you use the volume plus the bending constraints, you can see here that it will improve the results. Here what we see is the distance between the reconstructed point cloud and the theoretical model of the ground shape. And here with the volume you can see that the points at the beginning of the wing, where it's supposed not to move too much, are closer than when you use only the volume constraints. We can also see that using the mechanical limits will improve the stability by removing outliers. On this graph, what you can see is the reconstruction at the beginning with the blue cross on the background, and at the end of the motion sequence with the dots. Without the constraints, you can see that points are diverging during the motion sequence, and at the end you've got many outliers, while using the constraints, points stay close to their initial position within the mechanical limits. In conclusion, in this presentation we introduced a suited photogrammetry approach for the 3D estimation of the wing. We introduced a new constraint bundle adjustment that exploit mechanical limits of the wing to improve the 3D estimation, and we demonstrated the potential of this method through the realistic experimentations. Now the perspective will be to evaluate the method in flight with countermeasures, and to investigate the use of weighted bundle adjustment to reduce the influence of wrong observations. Thank you for your attention, and if you have any questions, feel free to ask.